Do you remember with derivatives, if you added or subtracted two different functions, you could just find the derivatives of each of them separately? We can do the same thing with integration. If you wanted to work backwards and you had two things added, you could just work backwards by doing one at a time. This is important because we realize that that doesn't work for derivatives with multiplication. And it most certainly won't work working backwards with multiplication either. But adding and subtracting, you can just do it separately. So if I had this integral, I could just do each one of these on their own. Do you remember the rule from yesterday? How to integrate these? Want to quickly write it down? I'll put the answer up. Or you want to do it, just like do it in your head. Then if you make a mistake, it's not in your notes. And you can check. So you wouldn't have to write this down, but I'm just showing I can do each integral separately. I would just go to the answer. Add 1 to the exponent and divide. Add 1 to the exponent and divide. A constant would just be a 2x. Does that make sense? And then we always have to write that plus c. So if you're adding and subtracting, you just do them separately. Same as derivatives, but it's an important property because it doesn't work for multiplying, it doesn't work for dividing. Question? You could, having it like that or without. Or you could have I could have had this as just a 3x and had the minus outside in front. Okay, but that second line, for the most part, you'll never write that because you will be able to just, in your head, go from there to there, not writing out a property in between. Okay? But sometimes there's going to be questions that will be manipulation type questions, where they don't give you numbers, but they might say numbers in some place and a function in another place, and then they want you to play with it. Then these properties become very important in those types of questions. Here we're multiplying. Oh my goodness. We don't have an integration property for multiplying. Sometimes, though, you can just actually multiply things out. If you actually multiply x plus 7 times x minus 3, which isn't too hard, you get x squared plus 4x minus 21, and then you can just do the integration of each one. Add 1 to the exponent and divide. Add 1 to the exponent and divide. Minus 21 will just be minus 21x. And then we always remember the plus c. So sometimes we have to do some algebraic manipulation first to make things work, because we don't have a property for multiplication. And you remember the power rule, the product rule for derivatives, how big and complicated it got? Things are worse in integration, because you have to undo things. And so when something's simple like multiplying, it is not simple to undo it. So in that case, we often manipulate to try to get it to look like something we can do. And that is a main strategy. Same thing in this one. It's dividing. I can't do that. Right? But what could I do? Right? You're stuck. You want to do the integral of this, and it's dividing. We have no rule for dividing. So we have to manipulate. Any suggestions of what you might want to try? A factor the top. If we factor the top, this is good. See what's going to happen? X minus 2 is going to cancel out so nicely. Makes me happy. So now we're just doing the integral of x minus 4, which is super easy, because we can do the x, add 1 to the exponent and divide. We can do the minus 4. And often, just like in derivatives, often in integrals, you're going to get radicals that are not easy to work with. What did you do with them with derivatives? You change them to exponents. What are we going to do the same thing with integrals? Change them to exponents. So first of all, I'm just going to take the time and change that to u to the 1/3. Does it bother you that your variable changed? Are you okay with that now? Can you use any letter, be fine. Usually there's a dx, now there's a du because it's telling you we have a new variable that we're doing the derivative with respect to. Sort of looks like, find the integral of u plus u to the 1/3. Duh. Like it's supposed to be super easy. Add 1 to the exponent and divide. So even if you have a fraction, you add 1 to that fraction, divide, and then when you're dividing by a fraction, you can take the time to multiply by the reciprocal to simplify it a little bit. But the AP, did Ms. LaFrance tell you, the AP is really not worried about simplifying whatsoever. Like way more than grade 12 was. Like if you left your answer, if the answer was 3, you could leave your answer as 1 plus 1 plus 1 and decide not to put that together, even though it's super easy. You could even, I wouldn't recommend this because they forced the person who's marking it to check, but you could come up with some 5-line expression that if you did all the math was equal to 3. And if the answer was 3, they would have to accept that. Although they would probably go, why did you do that? Why did you waste that much time coming up with something long and laborious? But if you are doing a question where you get something long and laborious and you're like, oh, I don't want to simplify this, just leave it. Make them check it. Make them type it in their calculator and see if it's the same number. Then you're going to be perfectly fine. So that always makes me feel a little bit nervous as a math person, be like, oh, I should probably clean this up a little bit and get a nice answer in the end. Property number 2. If you have some constant, like k is just a regular number, like 2, 3, 5, any number, and it's inside the integral, you can pull that k outside of the integral, just like we did for derivatives, right? For example, what's the derivative of 3 cos x? Right? Minus 3 sine x. Did the 3 matter? No, we just ignored it. Did you have to do a product rule with that 3? No. You just did the derivative of cos, and the 3 came along to the right. Same thing happens with integrals. If you have a constant, you can basically ignore it, you can bring it out in front, or just deal with it afterwards. Which is sometimes nice because, like, if I have an x cubed on the bottom, first thing I would do is change it to a power. And now I can just add 1 to my exponent. Oh, it says find the derivative. Ooh. You see what I did? We've been doing integrals for so long, I just assumed we were going to do an integral again. This is when life gets tricky and plays tricks on your mind because derivatives is one direction. Integrals is the other direction. And you don't pay attention for a second and it's very easy to choose the wrong one. So if you wanted to, the x minus 4, you could bring down to the bottom. But now if we're doing the integral, same thing. I could put that 4 inside, I could bring that 4 outside. But all I have to do for the integral is add 1 to the exponent and divide. You could simplify that if you wanted to, but you wouldn't have to. Maybe you tried the next one already on your own. If you want to write it out, I will put up the answer in a second. Check. How did you do? And you wouldn't have to simplify, but our next property might seem kind of obvious, but there's like a little interesting detail that's going to come up, right? If you do the integral of a derivative, the integral is the antiderivative, so it would get rid of what was already done. It would sort of cancel each other out. But if you do the integral of a derivative, so it cancels out, you just get the original function that you started with. But then you still have a plus c because you did the integral last. The next property is going to say if you do the derivative last, then there's no plus c anymore. So we have to be careful in which way that it's working. So this says do the integral of the derivative of 5x squared. So this d dx says do the derivative of 5x squared. If you did the derivative of 5x squared, you would get 10x. Right? So this question is the same as the integral of 10x. If I did the integral of 10x, I'd have to add 1 to my exponent and divide by 2, right? Which would obviously just get you back to where you started it. So the integral and the derivative would cancel each other out, but since we do the integral last, you would still need that plus c in the end. If you do the derivative last, so this says take the derivative of the integral of this, like personally, I wouldn't do this because it's doing extra work that you don't have to. Because once you add 1 to the exponent and divide, and then do the derivative of that, you're going to get exactly back to where you started from. Does that make sense? So I would see, hey, these things are going to cancel out. I'm just going to be left with 5x to the minus 3. But I have to decide, is there going to be a plus c with this one or not? So when we show the work, we can see that when you do the integral first, you get the plus c. But when you do the derivative of that plus c, it goes back to 0 because the derivative of just any number would be 0. And so you just get back to where you start with without any plus c. So it depends on the order that they're happening. And yeah, in my notes, I don't have that general result. I just gave you the one general result. You have both of them, both those general results in yours. And then at the bottom of the page, if you happen to be dusting at home and you find your calculus book, you could do some questions practice out of their table. Right? That would be if your math teachers didn't give you such beautiful take-home quizzes that give you lots of practice anyways. So on the next page, you have a big list. This list is super helpful. So helpful that I decided to choose a fancy color like money and print it out separate for you. So you're like, oh, where's that purplish colored paper? So that I can pull it out and feel guilty that I haven't memorized them all yet. This is what this is for. Look at the ones at the bottom. Should you feel guilty about tan inverse of x? I mean, we use it every day, right? The ones that are used the most, just a constant. 0 is really obvious. You just get c in the end if you integrated it. The 1 over x, the natural log, notice that when you integrate, you have the absolute values here. Because 1 over x could be any number, but you're never allowed to take the natural log of a negative number. Right? The domain of your log graph, if you imagine it, is only positive numbers. So in order to make that integral work, they put absolute values around the x. Then you're fine. E to the x, the wonderful one that doesn't change, which causes all sorts of headaches. And then a to the x. Remember the a to the x one? Where the derivative of a to the x was a to the x natural log of a. So now you have to undo that. So you have to divide by the natural log of a. Whew. Don't look so excited about it. Sine x and cos x. Those ones get used a lot. Secant squared a fair bit. These ones are a little bit trickier. I find the ones where you have multiple things to recognize that's only one thing a little bit harder to recognize because you focus in on one thing at a time. Now you have to look for, oh, but sometimes there's multiple things together that could work. And then the inverse ones are a little crazy. There we go. So let's try some on our own. Use your purple sheet. How many do I have there for you to try? A, B, 1, 2, 3. 3 questions. 3 questions to try on your own. Here, I'll put up the answer for the first one so you can check to see if you're on the right track. Here's the second one. Check that you remember the absolute value bars around the natural log. the last one. You want to go back to that previous one? Question, or is it about this one?